Another thing that's quite useful for the standard normal distribution is this table, okay? So I'm not going to fixate on this notation too much, as in reality, it's not really that common in the current spec. But once we have Z values, what we can do is we can use these to very quickly find probabilities. And this sometimes comes up in some problem solving questions. So let me just show you how you can use this. So I'd like you to pretend that we have just done some coding and we got a Z result of 0.5244. Okay, so the first thing to say is it's positive, isn't it? So because it's positive and 0 is in the middle, it means that the value is somewhere to the right. Okay, so this is about Z. But you'll see that this value seems to have a corresponding value in here, and it says 0.3. Well, what it is it's telling you that when you have a Z value of this, the probability left over to the right tail is 0.3. So we can work things out. And like I said, later this is going to be important for problem solving questions. So all of the values in this table are positive values because that's the way this table is designed to work. It says that when you've got the standard normal distribution, it's made such that the probability of being greater than this Z value is shown in the table. Let me show you one more example because it takes a few to get the hang of this. So if this is 0 again, because it's standard normal distribution, what would be the value here on the right that would leave only 5% left to the top right? Well, what I could do is I could identify that value and then say, well, this is the Z value that achieves it. So 1.6449, I think it is. Yeah, that is the value such that the area that's left is 5%. Again, the Z value is positive, so it's to the right. If it's negative, it would to the left. And I can use this to work these things out. What's not obvious is I can work out even more difficult things. So I can work out also while I'm here a value on the left. So what does the Z value have to be so that there's 30% less this time? Well, because it's symmetrical, I can do something quite clever. When it's 0.5244 is 0.3 to the right. When it's 0.3 on the left-hand side, remember anything to the left will be negative. It's actually this Z value that would achieve that. Similarly, if I wanted 5% less, well, I used the same number, but I just realized that to the right is positive, so to the left is negative, so it's minus 1.6449. So the values are written assuming that you have a positive Z, but they can be manipulated, and the diagrams below show you how you can manipulate them. In terms of this notation, this is not really something that we need to worry about too much because the new generation of calculators sort of take care of this for you. But this table is very, very useful, okay? And it is at the end of the formula booklet. So you just need to know how it works a little bit. So we're going to do some more quick examples. So what Z values correspond to? 50% of the data above. Well, that's going to be 0, isn't it? Okay, and you can see it in the table as well because it's symmetrical. 10% above. So 10% above will be 1.2816. 1% above. There we go. So that's an even more extreme value, yeah? So as I'm doing this, 0, 1.2816, 2, it makes sense. These are values that are getting more and more extreme. 50%, 10%, 1% above. So that was 2.3263. Let's write that down all together, 2.3263. 10% of the data below. Okay, well, it's symmetrical. So whatever this value is to achieve a 0.1 there is the same as this value here, but then the negative of that. So I think we've already got that, no? We can use this value to help us find this value here. This is 1.2816, so this must be minus 1.2816. And again, let's keep them all in the same place, minus 1.2816. 5% below, I don't think I have that yet. 10%, 5%. Okay, so it said below, right? So how about this? Minus 1.6449. Positive 1.6449 would be 5% above. This is 5% below. We're going to have a go then solving some problems. And what you'll find here is that they can turn into, as we're doing these, sometimes we're doing the table, sometimes we're doing the calculator, sometimes we can do both. So there's quite a lot of jumping around to the previous parts of the chapter. So this is normally distributed. Okay, so that's not a standard normal distribution. It wants to know what's going on in terms of z. So z equals x minus mu over the standard deviation. So 53 is like an x value, right? So what you want to do is you want to do 53. So let's write this out. So it's going to be 53 minus 50 divided by 4. That's what the z value will be, all right? So it's 3/4. So it's the probability of z being less than 3/4, okay? And in terms of the notation from the previous slide, we can write that, apologies, we can write that as this, okay? That's what the notation on the previous slide is about, okay? But, you know, in reality, we just use the calculators, like I said. And then we could work that out if we so desired. Okay, 55. So how do we do 55? So again, we would do 55 minus 50 over 4, which is 1.25. So it's the probability that z is greater than or equal to 1.25. Okay. If we wanted to use this notation, there is a way of doing it, but you know, quite frankly, I'm not sure that we really need to go over that again. All right, so that's how you could do it. That's how you could write it in the alternative notation. Let's try a harder example. So this is going to be the first time where we're probably going to be forced into using this table. Blood pressure of an adult population. So just bring my notes up in front of me. So blood pressure of a population is modelled normal. Okay, so it's normal with 127 and 16. A medical researcher wants to study pressures higher than the 95th percentile. So what that means is they want to know what this point is here, really, okay? So 95th percentile means 0.05 is left, okay? So it's a giveaway when people use this kind of language that you might want to use these tables because you've got 0.5, 0.4, 0.3, 5%. You've got lots of neat numbers here, okay? So what's the minimum blood pressure that we want to work with? So the minimum blood pressure is basically asking you, what's the x value that goes with the 95th percentile, okay? Now, there's a lot of ways we can answer this, yeah? Some of you may have already spotted that we can actually just use the inverse normal because we know the mean, we know the standard deviation, we know this. So we could actually just do inverse normal on our calculator for 0.95. Okay, but what they want us to do in this question is they want us to experiment with the z value. So I'm going to show you the z value approach. So we write our code, which is this, and we put in the information that we know. So x is the value that we're trying to find, right? Mean, well, we've got that. Standard deviation, well, we've got that. Well, you might say that we don't know the z either, but actually we do, because we know that when you want 5% of the data to be above, that's this bit here. So the value that corresponds to this is 1.6449. So if we substitute in all of these values, we can do a bit of problem solving. So we can say that 1.6449 equals X. So X means the blood pressure that corresponds with a Z value that corresponds with 5% of the data above. So we can turn it all into this problem here. And if we rearrange to solve this, we will get to three significant figures. We'll get 153, which sounds about right, yeah? If it's 127 in the middle, standard deviation is pretty big here. You know, it's 16 to the left and the right. That sounds like a fairly reasonable value. But this is an example of where, when you know percentages of data above or below, you can use these Z values, because how the data corresponds to 95% for the blood pressure is the same as the Z value corresponding to 95% as well. That's kind of the big idea. Let's do another one. So pause it for yourself, have a quick go. We are once more doing 115 as our key parameters. So what's the IQ? So the IQ is the X, isn't it, essentially? What's the IQ that corresponds to the top 10%? So top 10% has that Z value. If you're not sure what to do, write the code out. Z equals X minus mu over the standard deviation. So for part A, we're talking about when the Z value is a top, didn't it? So the Z score that corresponds to it is this, 1.2816. That's the Z value that goes with the top 10%, okay? And we can use this to find the X value. So that's the Z. X we do not yet know. This is 100. This is 15. And we rearrange, okay? So if we rearrange, we get X is equal to 119.24, okay? B, let's do B. So the bottom 20%. So the bottom 20%, what we're going to do is we're going to pick the top 20%. And what we said is the top 20% is 0.8416. So the bottom then is going to be the same, but the negative case, so minus 0.8416. And again, we repeat the same process, okay? So minus 0.8416 equals X minus 100 over 15. We rearrange and we would get our answer. And our answer for this one is 87.376 is what my notes say. Okay, so couple of sort of general tips. If you think you're going to be using the standard normal, you want to write this code down. And then there's a lot of problem solving about knowing 3 bits of information or knowing 2, using the table to get the third, but then solving this kind of problem. Okay, later in the chapter, we are actually going to do simultaneous equations with this, because the idea is that we're going to have a code where we don't know 2 pieces. We're going to make 2 equations to deal with it. And underpinning all of this, this visualization doesn't show up on great on here, but if I do have some original distribution and I code that, do you see how it looks the same? So that's useful because it means that a value that corresponds, say, with 0.4 here, yeah, also corresponds with 0.4 after it has been coded. So this is what we're taking advantage of at the moment, is that for any Z, there is an X, and vice versa, okay? So this is kind of the key theme of what we're using to solve the problems. So I think we will leave that part there. Let's do one of these problems. Let's leave this one for the next video.